homework key in my slides. Are there any homework questions from yesterday? Excellent, because it would have been the day I forgot to put it in the slide. What are we doing in class tomorrow? A quiz. It's over Mondays. You really have to warn people before you do that. You gave everybody a heart attack. Like the whole class, from my point of view, just went like that. Disrespect. And you improved the situation by slamming the door. So before somebody slammed the door, I was saying that the quiz tomorrow is on Monday and Tuesday's lesson, and it's not on what we do today. And I don't know if you remember on Monday when I passed out your new calendars, I said that there is some material left over from last unit, right? It's like Thanksgiving leftovers. That was Monday and Tuesday. That's the quiz tomorrow. Today we start new stuff. Today we move into talking about graphs of polynomial functions, and we will be continuing this even after Christmas break. So that is where we begin today. We have talked about graphs of functions before, like when we did transformations, right, of linear, cubic, absolute value, square root. Remember when we did all that? Those are just regular functions. But what we're about to do now is a specific kind of function called polynomial functions. And here's what's different about that. And well, first let's just review what polynomial means. It just means multiple terms. Okay, this is a trinomial. It has three things. So that's what we mean by polynomial. And these kind of graphs have a few characteristics that are part of their definition. It's these first three things right here. One, they're continuous graphs. That means there's no break or jump anywhere. Do you remember that day we did the cutting activity and then we taped the piecewise functions back together? We cut them on the domain and we taped them onto the purple paper. Those are not continuous functions. They quite literally had breaks in them because we cut them at certain parts of the domain. Bless you. So these won't be like that. The domain for all of these functions is going to be negative infinity to positive. Because there's no break, okay, it's just negative infinity to positive all the way. Bless you. And then these graphs will be smooth, okay? There will be no sharp turns. So we had one parent function that had a sharp turn in it. Which one is that? Which of the ones that we did before had a sharp turn? The absolute value. So remember, absolute value looks like a V. Excuse me. It changes direction right here. That is a point. It's a sharp turn. This is not a polynomial graph. And then this last thing right here is not actually part of the definition. It's just a little rule of thumb that we're about to use. So we've talked a lot this week about degree, right? Whatever the degree is, that's how many zeros there are, for example. When we're talking about degree on polynomial graphs, we have this little handy-dandy shortcut that says, if you're trying to find the degree, now this isn't an exact science, this doesn't guarantee the degree, it just tells you what the least possible degree is. You take the number of turning points on the graph and you add 1 to it. And that will tell you the least possible degree of the graph. So for example, in its most basic form, this is y equals x. How many turning points does that graph have? None. And when you take none and you add 1 to it, what do you get? 1. That's its degree. This graph has how many turning points? 1. And when you add 1 to that, what do you get? A degree of at least 2, right? And so we're going to use this thing I just highlighted. We're going to use it in this next example. And again, the point of today's lesson is we're just exploring properties of graphs, whether we're given pictures or whether we're given equations. We're going to be able to like Sherlock Holmes some stuff and figure out things based on context. So what we're doing here is you have 4 graphs, and underneath I arranged it on your note sheet. Usually we go this order. We go left, right, left, right. But right now what I want you to do is look at just the right-hand side. You see where it says A, B, C, D underneath? It has all that space, beautiful open space. This space is for you to answer this problem up here. And what that's telling you to do is determine whether each graph is the graph of a polynomial function. If yes, state the least possible degree, using that little shortcut I just told you a second ago. And if no, state why. So take a moment and do that, please, on your paper. What did y'all say for A, yes or no? I heard no. Hold on, I need a new color. This is no. I didn't get the color. This is no because why? What's your reason? There's a sharp turn. So I've been having some questions today about what constitutes a sharp turn. It looks sharp. It's like a point there. So some people have felt like these were sharp turns. I mean, they are kind of close to each other. The reason why they're not considered sharp is because it's more like smooth. There's no point there. Absolute value is a sharp turn. It turns at a point. Same thing here. It changes direction, or it turns there at that point. But even though this right here might look kind of sharp, it's not. Okay, upon further examination, you would find that it's curved. Okay. What'd you say for B, yes or no? Yes, it satisfies all the characteristics. And then yes wasn't enough. It also said to state the least possible degree. What did you put? 3. Very good. Because you're counting the turning points, which it turned direction in 2 places, and then you're adding 1. And so the least possible degree is 3. It might be more than 3. It's just the least possible degree that it could be. What did y'all say for C? Yes or no? Yes. And what was your degree? 4. Very good. There's 1, 2, 3 turning points. So you add 1 to that, and you get 4. And then did you say yes or no for D? It's no. And what was your reason? There's a break, right? It's on a break. Questions about any of those? Go good? All right. So that was picture form for determining these things. This right here, we also have pictures, so it's going to be really easy. This is asking us, this section right here is asking us to state the what of the graphs. The end behavior. Now, technically, mathematically speaking, what that's asking you for is this. It's asking for the behavior of the graph as x goes out to positive and negative infinity. And the behavior of the graph is another way of saying the behavior of the y values. What is y doing as x goes out to the extremes? So in this first graph, as x is going to negative infinity, what is the graph doing? Increasing or decreasing? Decreasing. So we would say that the left end behavior is going down. That's the left end behavior. And as x goes out to positive infinity, what are the y values doing? Increasing or decreasing? Increasing. So we would say the right end behavior is increasing, up. And depending on which math you've had before, which teacher, they have different preferences for how to write this information. I'm good with you just doing the arrows. And I will just assume that your arrow on the left is for left end behavior and that your arrow on the right is for right end behavior, because that makes sense. So just the arrows is really all I need. And so now, having said that, these next 2 problems are going to be the easiest thing you do all year besides putting your name on your paper. What's the end behavior here? Up, down. What's here? Down, down, just like the Led Zeppelin song. That was so easy, right? Okay, that was easy because you had pictures. What we're going to do now is how to find the end behavior when you just have a function with no picture, okay? How you can Sherlock Holmes that to figure it out. Now, this section here was going to be beautiful, and I was going to explain everything to you. This was the section I was going to be a fabulous teacher and lose you all in the process. So I'm going to skip straight to the shortcut instead of explaining it in excruciating detail to you. 7th period on Wednesday afternoon. So this shortcut is for determining the end behavior when you don't have a picture. Like if you look at the next slide, if you just have an equation or just a function, okay? You need two pieces of information. You need to know about the a value, right, the coefficient in the very front, and you need to know about the degree, which is the biggest exponent anywhere in the function. And you always want to look at your a value first. Here's your two options. Your a value can either be positive or negative. And when this is going to help us determine one specific direction, the right end behavior. When a is positive, here's an example for x squared. That's positive a value. Which way is the right end behavior going on that graph? Up. So for any graph at all, period, when a is positive, the right end behavior is going up. Okay, for any of them. And what happens to this example when a is negative? It's opening downwards now. What's the right end behavior there? Down. So when a is negative, the right end behavior is down. And that's fine. Now that's a shortcut for right end behavior. But you also need to know how to figure out the left end behavior. And in order to figure that out, you're going to look at the degree, right? And the thing you're going to ask yourself is the degree even or is the degree odd? When the degree is even, like this example up here of the x squareds, what do you notice about the end behaviors? What about their directions? They're flipped when a is negative. But they're both going in the same direction here, right? They're both going in the same direction here. If your degree is even, the end behaviors are the same. Same end behavior. Here's a graph of x cubed. The degree is odd. What's up with the end behavior here? Is it the same direction? It's the opposite direction, okay? So if your degree is odd, it's opposite end behavior. So the first thing you need to look at is A. Positive, negative determines if your right end behavior is up or down. The second thing you look at is the degree. Even means the end behaviors are the same. Odd means they're opposite. Now, before we talk about y-intercept down here, I'm actually going to go to the next round of examples, and we're going to practice end behavior. So you're looking at the first term. This problem wants end behavior and y-intercept. We'll do y-intercept in a minute. So is the a value, well, first of all, find your a value. And what do we care about? Is it positive, negative, or even odd? What do we care about? Positive or negative? What is it? Positive. So A is positive means what for the right end behavior? It's up. What's the second thing I need to look at? The degree. And what do I care about the degree? What specifically? Is it even or odd, right? What is it? Even. Even means what for the end behaviors? Same. So here's your, now I'm not writing that out every time, just for this one. Here's the actual answer I need. That the right end behavior is up, and then so is the left end behavior. I just need those two arrows. I don't need that whole explanation. I just put that there for you to see it one time. So we can tell that even without graphing the actual function or having a picture. Okay. You try B, just the end behavior for B. All right. First thing we ask ourselves is A positive or negative? It's negative. What does that mean for your right end behavior? Down. Second thing, is the degree even or odd? Odd. So same or opposite end behaviors? Opposite. So who got up, down there? All right, perfect. So let's talk about y-intercept now. We're going to be doing y-intercept in two different ways. One is this kind of form. What's this name of this form right here? Remember? Standard form. We've also worked with a different kind of form. Starts with an F and it's classroom appropriate. What's that word? Do you remember? Factored form. Oh, sorry. I'll get back to that in a second. So, factored form. Okay? So we're still going to talk about y-intercept, but it works a little bit differently depending which form you have. I'll get back to that in a second. Sorry. Here's what I want to review real fast, though, about y-intercept. Y-intercept means wherever a graph crosses the y-axis. That's what it means. Now, what is true about the x values everywhere on this y-axis? What do they equal? 0, right? So mathematically speaking, you can literally just let x equal 0 in the function, solve for y, and then I want you to always write your answer as an ordered pair. Right? Let x equal 0, solve for y, write as an ordered pair. Does anybody need that up anymore? I'm going to show you how to do this one time with almost excruciating detail, and then just show you the shortcut. So the y-intercept means you put 0 in everywhere you see an x. So it quite literally means this. But what happens to all of those terms where I just put that 0 in? They all equal 0, right? They just all get gone. They're gone. And that leaves me with just the constant, whatever number was at the end without any x's on it at all. But that's not how I want you to write your answer. How should your answer look? 0, 6 with the parentheses and everything. Okay, so it's a point. It's an ordered pair. Okay, so I had this question last period, so let me talk about that. So the question is, can we write y-intercept I assume you mean this, right? Equals 6. I would take that, but here's the risk you run. If you forget that intercept part and you give me this, y equals 6, I will not take it. And I will be picky about this because this is the equation of a line. Okay, it means something different. So that's why I don't want to take y equals 6. I want you to get in the habit of writing it as an ordered pair, especially if you're graduating and you're about to go off to college. If you're taking college math and your professor, whatever software, if you have to enter in answers online, if it's looking for an ordered pair, it won't accept y equals 6, right? Because, you know, it's a computer, so it's looking for exact form. It wouldn't accept that. So it's better practice to just write it like that. Does that make sense? Now the shortcut is this. You don't really have to put 0 in for all the x's. When you're in standard form, it's always going to be which piece, which thing for your y-intercept. The constant. Whatever that number on the very end is, with no x's on it, it's always just going to be that, because those will always drop off. So it's always just going to be this. Okay. But you can only do that when you're in standard form. Because we're about to be in what form? Factored form, and it works slightly differently there. Does anybody need this up anymore? Okay. So I had this little brain break in here. Now this was in my slides from last year, maybe even the year before. I know it's old, but on the off chance you've never seen it before, it's kind of funny. It says, my mom still hasn't noticed. That's behind the thing. Do you see it? This is the Yoda. He doesn't belong. I thought it was funny. Because it's almost Christmas time, I thought it was funny. Okay. All right, so this is similar to what we just did, but it's with factored form. And it's asking us one additional thing, the degree. We still want to know the end behavior, and we still want to know the y-intercept of the graph, okay? Now here's the thing. To figure out the degree, we need to know the degree. To figure out the end behavior, we need the degree and the a value. What we could do is this. Don't write this down. I just want to show you something. We could say, oh, okay, x plus 2 cubed means this. And I could FOIL and do box method and multiply until 9 o'clock this evening, and then finally have this answer, right? And then I would know the a value, and I would know the degree. But we don't have to do all of that just to find the first term. So we're not going to do all that. What we're going to do instead is just multiply out the first terms in each factor. So this first term gets cubed. And then that first term in the second factor just is to the first power. Okay. And so what is x cubed times x? X to the fourth. This is the same thing you'd get even if you multiplied everything all out long. All right? And what's the a value there? I don't see one. I just know that it is 1. So that's all the information we need to figure out the degree and the end behavior. We don't have to have all that other stuff that would go along after it. So for the degree, that's easy now. We know the degree is 4. And then for end behavior, is a positive or negative? Positive. So the right end behavior is which way? Up. Is the degree even or odd? Even. So the left end behavior is same. Very good. Now the y-intercept. If we had FOILed and box method and multiplied till 9 o'clock and had the entire function written out, we also would know the constant, right? And we could just pick it off and use the y-intercept. But we don't want to do that. We can still just plug 0 in for x, just like the last time. Technically, that's what we can do. So just imagine those x's drop off, and that would leave you what inside the first set of parentheses? Just 2, right, if x was 0. So basically, you're just now multiplying the last terms to get the constant. So if you want to leave a little note to yourself, though, let x equals 0. And then solve for y. So this would be 8 times negative 3, which is negative 24. And then write it as an ordered pair, which is 0, negative 24. And I'm going to give you a couple minutes to try B with one hit. Hi, thank you. Do you see that negative up front with your eyeballs? Leave it outside for while you do your math. It's not inside any of the factors. You're not going to distribute it into that first factor because distributive property doesn't work with the powers. Distributive property is defined with linear only. So do not distribute that. Just leave it on the outside while you do your math. Okay, and then take a few moments and try that. See what you come up with. Okay, because I don't want you to get too far before making sure you're on the right track. Did you get negative x to the 5th for the first term? I want to be sure you got a negative. The negative is not part of the squared at all. It's because it's not inside of the parentheses, okay? And the reason why that's so important is because if your a is negative or positive, completely changes what answer you come up with. So the degree is what? 5. And then for the end behavior, because a is negative, the right end behavior is what? Because the degree is odd, the directions are opposite. Right? So up, down. See you tomorrow, Bentley. And then for the y-intercept, do not forget the negative that's floating out front. It's still part of the problem. And then in the next parentheses, it's 1 squared, and then 3, and then negative 6. And be careful with your order of operations, because the negatives are going to be tricky. So order of operations, you do exponents first. So you're going to do that 1 squared. That negative is outside the parentheses, therefore, it's not squared. Just the 1 is squared. So that negative is still out front. Then you multiply all the way across. Positive 18. Good? Questions? Okay, we are not doing the rest of the problem. Yes. And the reason is because